Okay, today we're just going to do two problems to help you get used to using vectors and how to operate with them. Okay, so here's example 6 from our book. Consider a weight of 50 pounds hanging from two chains as shown in the picture. One chain makes an angle of 30 degrees with the vertical and the other an angle of 45 degrees. Find the force applied to each chain. Okay, so here's what we're going to do. We're going to make what's called a free body diagram, which is a simplified picture showing the different forces at play. And force is a vector because force has a magnitude and a direction. Okay, so what I'm going to do is I'm going to draw just a little square here that's going to represent our weight. Okay. When I say our weight, I mean that object hanging. I don't mean 50 pounds. I mean that object. Okay? Now, there's three forces acting on this. Number one is the actual weight of the object, and that's a force that's pointing down. Okay? Let me see if I can straighten that up a bit. Oops. Hold on. Let me redo that arrow. Try and make it more straighter. Okay, so that's the weight of the object is pulling down. Let's call that force Fg. And that's a vector. Okay, there's also two other forces, and that is the chains pulling up on the weight. How is it that the chains are pulling up on the weight? Well, very simple. If they weren't, the weight would be falling. If gravity is pulling down on the weight and nothing's pulling up on it, then the weight would fall. The fact that it's hanging there means it's not falling, and so there must be some upward force being pulled on it to counteract the force of gravity. Okay, and the only force that can be pulling up is what we call tension through the chains. Okay, now there's one chain hanging. Let's do this. Okay, I'm just going to draw. Nope, that's not what I wanted. I'm just going to draw a dashed vertical line here. Okay, now there's one chain that's hanging 30 degrees to the left of that. Now this is not the chain that I'm drawing here. This vector is not the chain. It is the force of tension that is on that chain. Okay? And we are told that this is a 30-degree angle. Okay? And there's another chain hanging 45 degrees to the right of vertical. These arrows here, these vectors, are not necessarily the same length. Okay, that's very important to understand. One might be shorter than the other. Because remember, these arrows are not the chains. They represent the force of tension on each chain. So the direction of those vectors matches the angle of the chains, but the length of those vectors don't necessarily match the length of the chains. In fact, they almost certainly don't, because I wouldn't expect the magnitude of the tension force to happen to be exactly the same length as the chain. The force is applied across the whole length of the chain, but the strength of the force does not equal the length of the chain. Okay, so let's call This one on the left, let's just call that force 1. And the other one, let's call force 2. Okay. Now, let's write down some magnitudes for those forces. We know the force of gravity is pulling on this mass with a strength of 50 pounds. So I write the magnitude of Fg equals 50 pounds. Now the magnitude of the forces on the chains we don't know. So let's do this. Let's call the magnitude of force 1. I said that those kinds of forces is called tension. So let's just call that one T1. And the magnitude of force 2, let's call that T2. Okay? Now, look at the downward force. Imagine an XY axis there. Imagine that those forces are all emanating from the XY axis. Okay? How would you write the downward force? Do you agree that it would be this? Zero, negative 50, right? Because it's pointing straight down with a length of 50. Remember, the magnitude of the force is represented by the length of the arrow. Okay? So that's our downward force. What about the force of tension that's pulling up 35 degrees left of vertical? Okay, that one's a little bit harder. Here's what we're going to do. Let's decompose that into a vertical and horizontal vector. Okay, so watch what I do here. Let's draw a vertical vector straight up to here, and a horizontal vector across here. Now, do you see that force 1, that black arrow, is the sum of the red and the green vectors, right? The length of the black arrow, let's write that in gray. The length of the black arrow is T1. Let's make that not so thick. So how long is the red arrow? I think you already know, don't you? Wouldn't the length of the red arrow be T1 cosine of 30 degrees? How long is the green arrow? The green arrow is a length of T1 sine of 30 degrees. So the red vector has this length and it's pointing directly upwards. So the red vector is 0, comma, T1 times cosine of 30 degrees, which I hope you know is root 3 over 2. Let's do this. Let's actually leave it as cosine 30 degrees because I want you to get used to seeing that. Okay. And what's the green vector? The green vector has a length of this and is pointing horizontally to the left. So doesn't that mean that the green vector would be negative t1 sine of 30 degrees, comma 0, correct? And the vector f1 is simply those two vectors added together. So we get f1 equals the vector negative t1 sine of 30 degrees, comma t1 cosine of 30 degrees. That's our vector f1. Okay? Now, let's find vector f2, doing the same idea. We're going to, this is called decomposing it into its horizontal and vertical components. Okay? So this time we're going to have the vertical vector looking like this, the horizontal vector looking like this, okay. How long is that red vector? It's t2, so let's write the t2 down, by the way. The black vector has a length of t2, and that's the hypotenuse of a right triangle. The red vector would be, whoops, the red vector would be t2 cosine of 45 degrees, and the green vector would be t2 sine of 45 degrees, just using trigonometry here. So the red vector is pointing straight up with a length of t2 cosine of 45 degrees. So that vector would be 0, comma, t2 cosine of 45 degrees. If you're using degrees, you always say degrees after you say the number, because if you don't say anything, then that automatically means you're doing radians. And of course, we don't want 45 radians. That would be huge. Okay, the green arrow is pointing horizontally left with a length of t2 sine of 45 degrees. So that green vector is the vector t2 sine of 45 degrees, comma 0. And we add those two together to get f2, and that is going to be the vector t2 sine of 45 degrees, comma t2 cosine of 45 degrees. Okay. Let's go ahead now and erase these colored things. We don't need those anymore. Okay. Now, here's the key. The key is that the net force on that mass is 0. Let me explain why. So, First of all, what is net force? The net force is the sum of all of the forces acting on the mass. So our net force is F1 plus F2 plus Fg. That's the net force. Okay? Now, that must equal, in this case, the zero vector. Those three vectors must equal the zero vector. And here's the reason why. One of Newton's laws of motion says that force equals mass times acceleration. We have a mass there, but it's hanging still, which means it's not accelerating. Force equals mass times acceleration. If the acceleration is 0, then that means the force has to be 0. So there are three non-zero forces acting on our mass, but the net force, which means the total combined force, is 0. If it were not 0, then the mass would be accelerating in some direction. The fact that it's hanging still means it's not accelerating, which means there's no net force acting on it. So that's why I wrote that the sum of the individual forces has to equal 0. Another way to say it is that those three forces cancel each other out. Okay? Okay, so let's write that out. Here's F1, negative T1 times the sine of 30 degrees, so that's negative 1/2 T1, comma, T1 times the cosine of 30 degrees, that's root 3 over 2 T1, there's F1, plus F2, which would be root 2 over 2 T2, comma, root 2 over 2 T2, plus Fg, which is 0, comma, negative 50, equals the zero vector 0, 0. So that tells us that this plus this plus this equals 0, and also this plus this plus this equals 0. Let's write those two equations down. This is the equation we get from the x components, and here's the equation we get from the y components. Or some people prefer to call those the I and j components. Okay, let's simplify that. So we have negative 1/2 T1 plus root 2 over 2 T2 equals 0. And root 3 over 2 T1 plus root 2 over 2 T2 equals 50. Now, anybody should be able to solve that. This is a college algebra problem, right? A system of two equations. And by the way, we can even make it nicer by doubling everything to cancel out the fractions. If you double both sides of the first equation, it becomes negative T1 plus root 2 T2 equals 0. And double both sides of the second equation, you get root 3 T1 plus root 2 T2 equals 100. You guys can solve that. Okay. That's just algebra, so I'm going to tell you what I get, but I would leave it to you to check that and actually work it out. Okay. What I came up with solving that was I came out with T1 equals 100 divided by 1 plus root 3, which is approximately, by the way, that's going to be in pounds. That's approximately 36.6 pounds. And for T2, I got 50 root 2 over 1 plus root 3 pounds. And that's approximately 25.88 pounds. Okay, so now we know that if you take a 50-pound weight and you hang it from 2 chains or ropes or something at angles of 30 and 45 degrees off of vertical, then the tension on the one rope will be 36.6 pounds and the tension on the other rope will be 25.88 pounds. Okay? Let's do one more that's essentially the same type of problem, just more practice, okay? Let's look at this one, example number 8. So now you have a weight, which this one happens to weigh 25 pounds. Well, let me just read it. A weight of 25 pounds is suspended from a chain of length 2 feet. So let's write that down really quick. This is 2 feet right here. I know in the picture it might be confusing because of this saying 2 feet, but that goes from here down to this dotted line. That's 2 feet. If the wind was not blowing, then this chain right here would be straight up and down, and the top of the weight would be right here. Okay? Which means that that chain is 2 feet long. And then when the wind blows, we haven't got there yet, have we? A wind pushes the weight to the right with a constant force of 5 pounds. Okay, and when it does that, the weight swings to the right, but the length of the chain doesn't change, and so the weight goes up a little bit as it swings to the right. I think that makes sense, right, if you think about it. So the important point I'm trying to make for you right now is that this is 2 feet long right here, okay, which is the hypotenuse of this right triangle. Okay, what angle will the chain make with the vertical? So they want us to find theta. And how much higher will the weight be? So they want us to find this distance right here. Okay, let me show you how to do that. Very similar to the last problem. Let's make a free body diagram. There's our mass. Okay, what are the forces acting on that mass? We've got gravity pulling down. So we'll call that Fg, just like last time. Okay. And let's go ahead and write down what that vector is. It has a magnitude of 25 pounds and it's acting straight down. So that's going to be 0, -25. Okay? Now, there's a force of wind, which is going this way, right? But remember what I told you is that vectors are the same no matter where they're located. Just the magnitude and the direction is all that matters. You have to be careful though. Here, this is a word problem, so it does matter where the force is acting on. That location does matter. But the point I'm trying to make is, what I want to say is that we can take that, it's acting on the center of mass right there. Okay? I can draw it right here. Whoops. Try to get that there. Stop right there. That's good enough. So I can draw it like that, but it's easier for me to understand, I think, if I draw it like that. And it does not make any difference. I'm not saying that the wind is blowing away from the weight. That's not what I'm saying. I'm saying the wind is acting on the center of mass of the weight, and it has a magnitude of 5 pounds and a direction that is to the right. Okay? So I'm going to do this. I'm going to write vector FW equals, what would it equal? It would be 5, 0. Okay, what other force do we have? We have a tension force from a chain. Whoops. Right about like that, correct? At an unknown angle to us, off of vertical, we just call that theta. Okay? Since there's only one of those, let's just call that Ft, since it's a tension force. Now, how long is that? Alright, here's what we're going to do. I'm going to decompose it into vertical and horizontal vectors, just like we did in the last problem. Okay, a vertical vector, a horizontal vector, the black vector is the red vector plus the green vector. How long is the black vector? Okay, now you gotta be very careful. It's not 2 feet. In fact, feet wouldn't even make sense. That's a force. It's not a length, it's a force. So the units would be pounds. And remember what I told you earlier? That black vector is not the chain. It is the tension force on the chain, which means it acts along the direction of the chain, but the strength of the force does not equal the length of the chain. So the length of that arrow is not necessarily the same as the length of the chain. In fact, it almost certainly won't be. So what do we call it? Well, we don't know how long that vector is. So let's just call it the length T. T for tension. Okay? So how long would the red vector be? Very similar to last time. The length of the red vector would be T times cosine theta. And the length of the green vector will be T times sine theta. That's just using trigonometry. So the black vector equals T cosine theta comma t sine theta. Does that make sense? We're just taking the red vector, which would look like this. Oh, I made a mistake, didn't I? I just realized something. I'm missing a minus sign. We're taking the red vector, which is that, and we're adding the green vector, which is this. So I made two mistakes, didn't I? I should have written it down to start with, because this is totally wrong. I got the components switched, and I forgot a negative sign. It should have been negative t sine theta, comma, t cosine theta. Okay, well, there's a good lesson to write down what you're adding together to make sure you add it correctly, because I didn't pay attention to the order that I was writing those two components, which was silly of me, and I also forgot the fact that the green one is pointing to the left, so that component is negative. Okay, so there we go. And now, just like before, if the weight's not moving, now you might say to this, you might say, well, if the wind is blowing against it, it would be moving because it would be rocking back and forth. That's true, it would in real life. But they have said here something that's not very realistic, that the wind is constant. Wind does not work that way in real life, does it? It's always fluctuating a little bit. But they're trying to explain a situation here where this is probably in a wind tunnel or something, you know, it's not hanging outside on your porch. And so they've manufactured in such a way that the wind is perfectly constant. So this thing would move to the right, but it wouldn't be swinging back and forth. It would be sitting still. And that means, since there's no acceleration, then once again, there's no net force. So we write the sum of the forces must equal the zero vector, which is saying that those three forces are canceling out. The tension on the chain is canceling out the forces of gravity and wind. Okay? So let's write down that equation then. We have negative t sine theta, comma t cosine theta, plus 5 comma 0 plus 0 comma negative 25 equals 0, 0. So that gives us two equations. These three components add up to 0, and these three components add up to 0. So I can say negative t sine theta plus 5 equals 0, and I can say t cosine theta minus 25 equals 0, which I think is easier if we do this. Let's write it like this. T sine theta equals 5, and t cosine theta equals 25. Now, how are you going to solve this? You should all be able to, but it is a little bit harder than the last one because it's got some trig in it. So I'm going to work through this one with you. Let's square both equations. We get t squared sine squared theta equals 25, and t squared cosine squared theta equals 625. Let's add those together. That'll give us t squared sine squared theta plus t squared cosine squared theta equals 650. But on the left, I'll factor out a t squared. What's sine squared theta plus cosine squared theta? That's 1, isn't it? So this is just t squared equals 650. Which means that t is the square root of 650. Which I'm going to choose to simplify. That's 5 times the square root of 26. Okay, now let's go back to the question. Did they ask us for that? They didn't, did they? They just said, what's the angle theta and how much higher will the weight be? So that's not my final answer. Okay, but let's remember these two equations right here. And let's pick one. I'm going to pick the cosine equation. I like cosine a little bit better than sine myself. I have t cosine theta equals 25. And now I know how strong t is. So I can write now 5 root 26, that's t, times cosine theta equals 25, which means cosine theta equals 5 over root 26, which means theta is the arc cosine of 5 over root 26. And we can calculate that on a calculator. It comes out to be about 11.31 degrees. Whoops. So that's our first answer. The angle that the weight moves is an angle of 11.31 degrees. Okay? Now the next question says, how much will the weight go up? Okay, for that, we're going to look not at our free body diagram, but at the original picture. We're going to look at this triangle here. That's different than this triangle because the length of this hypotenuse is 2. The length of this hypotenuse was something else. Okay? All right. So I'm just going to do this. Let me write that 2 neater. Okay, so I'm just going to take this here and zoom in on it. Okay, looks like this. And we know the hypotenuse is 2 feet long. Let's find out how long this is. We also know this angle, by the way. Theta. It's highlighted down there. It's the arc cosine of 5 over the square root of 26, which is about 11.31 degrees. Okay? So how long is that question mark length? Okay, again, trigonometry. That question mark has a length of 2 cosine theta. Look here. There's cosine theta. 5 over root 26. So that's going to equal 10 over root 26. Okay, and that is about 1.96. And that's in feet because the 2 that I got was measured in feet. So that's about 1.96 feet. So how much did the weight go up? The weight went up by whatever is the distance. I mean, not distance, difference between 2 and 1.96. So that's 0.04 feet, which is about 0.47 inches. Just multiply 0.04 times 12, and you get approximately 0.47. In the book they say about 1/2 inch, but our answer is more exact than theirs. Okay, so the angle that they asked for is about 11.31 degrees, and the distance, how much higher will the weight be, is about 0.47 inches. These are very, very good problems to get you used to working with vectors. It is going to be important. Vectors are going to be with us for most of the rest of the class, I expect. Okay, I hope that makes sense. Have a good afternoon.